And then after the platelet phase, you have the coagulation phase, and this is where things get very complicated. Like in that anime, they say they have like these little metal canisters. They make it very easy. Like they kind of gloss over this part because, and I think they want to gloss over that part because it can get very dry and very complicated. So this is what happens during the coagulation phase. Well, when you have that injury, that injured the surrounding cells and also the extracellular matrix of the tissues surrounding the vessels. So all of these cellular contents of the cells that line your blood vessels, as well as the tissues that are around your blood vessels, these send chemical signals that activate different enzymes. So what we have here is tissue damage activating the sequence of enzymes and factors. These are all protein factors, well, except for calcium, that's an ion. And then you have two main pathways. So we have like, and now this is the other thing. Do I want you to know, okay, with the extrinsic, what's intrinsic? That's maybe more advanced. What I want you to know is that, okay, these are activated by the cellular and molecular damage to the vessels. And what happens is that they both converge on a common pathway. So all of these enzymes are being activated in sequence, but they end up in something called the common pathway. And this is what I want you to focus on at this level. So factor X, the X factor, this is the first step of the common pathway. So regardless of the injury, whether it's extrinsic or intrinsic, it will activate factor X eventually. So factor X, what will that do? It activates this, or actually converts this enzyme or protein, prothrombin, into an active enzyme called thrombin. Thrombin converts this protein fibrinogen into fibrin. And fibrin is actually what forms this fibrous protein patch that helps to seal up the little cracks between these platelets. So it's kind of like the platelets are the bricks, and fibrin is like the mortar that kind of like helps to seal the areas between the bricks. So yeah, the coagulation cascade. This is like if you go on to advanced A&P, and especially if you go on to medical school, you'll have to know the coagulation cascade. And this is a typical, I think this is probably off like Creative Commons / Wikimedia. And yeah, so what we see here is that most of these are protein factors, and these are all, well, again, calcium is an ion, not protein. But most of these are proteins produced by your liver, and these are all, what they do is activate each other in sequence. And then what they do is basically kind of like enzymes that chop up other proteins to make another active enzyme. So it's like a domino effect. It's like a chain reaction. One enzyme cleaves another protein to make another active enzyme to make another active enzyme. So this is what the coagulation cascade is. And that's the simplified version. This one actually has feedback loops and negative feedback loops. Now this is more if you're going to like a doctoral research, or if you're going into more molecular biology, maybe you'll have to know this one. But again, I'm going to choose my targets keep it simple at this point, especially this part with the common pathway with factor X. That's what I want you to focus on more. And even in the OpenStax version, it's a lot, I think it's simpler than the other figures. But notice that, again, what you have here is that you have factor 12 activating factor 11, activating factor 9, which helps activate factor 10. And the extrinsic, you have factor 3 activating factor 7, activating factor 10. And then, yeah, so factor 5 gets, and then 2, 1 here. So I know that's a lot. For this one, focus on the common pathway right here, because again, regardless if it's intrinsic or extrinsic, you have factor X being activated in order to form the fibrin clot. So this is what we have here. So factor X is a prothrombin activator. So it takes prothrombin, which is inactive, and then cleaves it to form an active enzyme called thrombin. Now thrombin itself is an enzyme, and it's going to convert fibrinogen into fibrin. And fibrin is the protein that ends up patching up the little cracks between all these platelets right here. Alright, so the thing is that, remember that blood is a special connective tissue. It is a fluid connective tissue. And connective tissues, they have three things in common, right? They have cells, they have protein fibers, they have ground substance. But again, not only is, remember, blood is fluid, right? So it has, instead of extra solid protein fibers, it has extracellular proteins, but not only are they extracellular proteins, they are water-soluble extracellular proteins because, again, these proteins need to float around in your blood. Otherwise, if they didn't, they form solid structures in your blood, they would form clots, they would form blocks, they would form embolisms. We're going to get to that real soon, by the way. So here's like a lining of a blood vessel, and here's your bloodstream. And oh, we have an injury here. So what happens? So what we have here are all the platelets. This is during the platelet phase. They're trying to form a plug, and they are blocking the outflow of blood and hemorrhaging to a bit. But you need something to seal in the cracks and kind of solidify that clot. So what we have here is fibrinogen. So fibrinogen in its original intact form, it's water soluble. So again, if you don't want to form a clot, you need the proteins in your blood to be water soluble so that they can flow throughout your blood. Now, in the previous one, when we had factor 2 being activated, we have factor 2, aka being activated into thrombin. So thrombin is an enzyme. So again, a lot of enzymes end with ASE, but there are exceptions like thrombin. Thrombin is an enzyme, but doesn't end with ACE. So what thrombin does is it takes fibrinogen, which is water soluble, and then it converts it into fibrin. Now fibrin is insoluble, so it's not water soluble. So what happens to substances that are water insoluble and you throw it into water? Well, if it's insoluble, it's not going to dissolve, it's not going to flow, it's not going to form an even suspension, right? So what it does is fall out of solution. So if you have this thrombin here at the site of the clot, and then you have it converting fibrinogen to fibrin, this fibrin is going to stick, and not only is it going to stick, it's going to stick to things like cell membranes, because again, cell membranes have that hydrophobic component, but it's also going to, as you make more and more fibrin, this fibrin is going to stick to each other. So the fibrin is going to form a mesh-like network that helps to patch in the areas between the platelets. So this is why not only do you need platelets, but you also need fibrin to form a watertight or hydrophobic patch that helps to seal it. So it's kind of like that commercial where you see that guy has that, what's it called, Flex Seal, and there's that tank leaking all the water. He just takes that duct tape and just smacks it on there, and it stops the leak. So that's what fibrin is kind of like. It's like duct tape. So you have the platelets trying to plug it in, but now the fibrin's like duct tape helping to seal up that leak, seal up that hemorrhaging. Alright, so then coagulation cascade. So why is this important? Well, again, it helps to form the final fibrin clot. So you have that thrombin, and what it is it actually has an ACE. So it is a type of enzyme called serine protease, again, an enzyme. But what I'm getting at here is that all these activations of these factors, you're basically taking by chemically altering and cleaving these proteins that make up these enzymes, you form an active enzyme that activates another enzyme that activates another enzyme. So this is what the coagulation cascade basically is. It's a bunch of proteins that activate each other in sequence, forming these enzymes that help to convert fibrinogen to fibrin that helps to finally seal that clot.